Hi everyone, welcome back to my video series Agile Development 101. Today we're going to talk about two interrelated topics. The first is emergent architecture and the second is separation of concerns. Emergent architecture is more of a strategic um, technique which is a typical Agile technique. Basically, it means that the architecture of your system, not only hardware, but also software libraries that you use, the structure of your code, and so on. Not every decision has to be taken up front, and it's actually better not to take too many decisions up front. It's better to make good incremental decisions based on the information you have on hand at any given time. So today, I might need a way to store data. So I should think about where am I right now, where do I think I'm going, and what is the minimum decision I have to make um, in my architecture. And based on that information, I make a choice. And that choice can be, it can be long-term thinking. But I don't have to go and make additional choices and lock myself into something just because I'm talking about a data layer, just because I'm talking about a database. So it's about incrementally allowing the architecture to emerge as information about the product emerges and gets discovered. Now, this incremental architecture has the potential to get messy. We add a library here, we add a library there, our code gets all mixed up and jumbled, which is why, to combat that type of thing, which is essentially technical debt, to combat it, we enforce separation of concerns. And separation of concerns means that code is divided up. It has certain boundaries which determine what goes where. Certain things like business logic should all be contained in their own files and should not touch other things like the view layer, how things get displayed on the screen. They have to interact somehow, but those bindings should be agnostic of the other end. It shouldn't care how it gets there, just that it gets communicated in a consumable form. And so this is called separation of concerns. What we'll do next is we're going to look at the traditional um, architectural model for an application, which is MODEL-VIEW.CONTROLLER. This is a typical model for any sort of user-interacted application, anything from a video game to a e-commerce site. There are other types of software which don't have this pattern because they may not have a user. They may not have any data in them. But typically, the vast majority of applications fall into this category. And this is a pretty good mental model of how the application gets structured. So let's walk through this pattern. The first thing is the model, which is let's take the example of an e-commerce site. In the e-commerce site, there's probably a SQL database holding all of your product information and customer information and transactional information. That model, that SQL database is the model. Then a client on a web browser connects to the website and says, hey, I want to look at this product. So the model sends an update down to the browser with all this data information about the product, and typically it's already pre-rendered, right? The format and the HTML is all put together on the server, and then it's delivered as a package that the view layer just dumbly displays with no intelligence. So then it turns into the view. So you see a web page on your screen, you see it, you're the user, and then you interact with it somehow. You click on a link, you push a button, you type in a field. Whenever you perform an action, you use the application. The business logic of how the application should respond is determined by the controller. So it might say, if your order is over $100, apply a 10% discount. So this logic probably needs to be validated on the server because it's sensitive, but some of it might happen on the client as well. That's all contained in the controller. And then the controller, when it needs to make changes to the database, it sends a message to the model and it manipulates the database. So it goes in this loop like this. And all the code for the database is held in, segregated out into their own set of files. All the code for the view is segregated into its own files, and all this code for the controller is segregated into its own files. The user doesn't have any files. So this is a pattern. It's not a comprehensive architecture for any application. Every application is going to have additional things and nuances and libraries and details that aren't fully captured here. But this is a good guideline for how to divide up your code. And so next I'm going to show you my take on the current architecture of Agile Freight. There's a lot more boxes in here, and it probably looks overwhelming, but this is something that our developers should probably understand so that when they make decisions on architecture, they can understand the impact of those decisions. This can change every sprint, but the current state is important because every developer is expected to enforce this pattern, at least until it changes. So let's walk through the flow. In the top right corner, we have server data. I segregate server data instead of just saying data because there's data on both the client and the server. So this could be a database, it could be multiple databases, it could be file stores, it could be a graph database, could be anything. In our application, it's a NoSQL database using MongoDB. Whenever a client connects to the server, the client subscribes to a set of data, and then the server reconciles any differences between the client and the server. So in the beginning, there won't be any data on the client. So the server has to send all subscribed data to the client. This is the reconciliation process. So then the client data gets filled out. Data is just sitting in JavaScript somewhere. It's not doing anything unless it somehow interacts with the application. So the first thing that happens is that once the client data is loaded into the client data store, it creates an action. And this action gets dispatched to a set of functions called reducers. Okay, these functions determine how the local state of the application should look based on a set of actions. So it sounds complicated, but for loading data, it's quite simple. It basically just, let's say you're viewing a page of a quote, it will take that quote data and stick it in the reducer says, take this quote data and update the store, stick it in the store, as is. Okay? So it goes through this reducer function, sticks it in the store. Then the store updates our view layer, which is basically the HTML, which the user then sees. Then the user can do one of two things. The user can initiate actions which will change the local state of the application, but does not affect the server state. So that's like editing a document before you press save. You type in a field. It doesn't need to be stored on the server yet. It only needs to be stored in the application. So when I act on local data, as in type in a field without pressing save, it will again generate an action, which gets dispatched to the reducer, which updates the store, which then updates the view. So we go in this loop, this one-way loop constantly as interactions happen. But sometimes we do initiate an action which affects server data, like pressing the save button. When you press the save button, you expect that saved document to go to the server and be reflected in the database. So what happens is that you act on remote data, and then two methods get fired at the exact same time. Well, almost the same time. The client simulates the update on the server, but it simulates it on the client itself. And then the server performs the actual update. So these both get fired. They both update their data. But what if they don't match? If they don't match, then the server reconciles down to the client, and it corrects any errors. This is the optimistic UI part of the architecture. The client doesn't need to wait for the server to update. The client will update the data will update the store, it will send out an action which dispatches to the reducer, which updates the store. And then at some point down the line, there will be a response from the server which says, your data is correct or your data is not correct. And if your data is correct, nothing happens. And if your data is not correct, then it will dispatch another action, which goes to the reducer, which updates the store, which updates the view. In the vast majority of cases, the data is the same on both the client and the server. The other thing that could happen is that two people are logged in to the application at the same time, and one of them changes something, saves a change to a quote, and they're both looking at the same quote. Then what happens? The server data has changed, and there's this reconciliation process which will happen on both machines. Even the guy who's looking at it, who did not edit anything. And the server data will reconcile down to the client data, which will generate an action which will update the store and update the view. That's the reactivity part of the architecture. And so that's optimistic UI and reactivity. We have this other green box called deterministic local state management. So this is a concept which is meant to help with creating UIs that are easy to debug and easy to predict. So deterministic means given a set of inputs, the output is known. Now, in a lot of architectures, there are something called race conditions. There are asynchronous actions happening, like data being loaded, like the user clicking on something, and they could all resolve at different times, right? Because it's waiting for something else to happen. And whenever you're in an application like that, it's very difficult to reproduce any kind of bugs that appear because it's all based on timing, which might be based on your internet connection, which the developer doesn't share. It causes a huge, huge headache. And any developer who's worked on this knows this. It is such a pain, and everyone wishes there was a better way. And there is a better way, which is deterministic local state management, meaning any kind of anything that's going to change the local state must be passed as an action to a reducer. This reducer is a special function called a pure function, meaning that there are no side effects. Well, there are no side effects from the function. Every input has a given output. Basically, regardless of when it fires or under what context it fires, it always returns the same result, which means that it's deterministic. The system is deterministic, and we can recreate any bug that anybody ever generates because any kind of interaction has been through this deterministic model. That sounds really complicated. There's a lot of reading material on this type of thing, but basically I'm using some libraries that help me do this. Okay, so this is my architectural pattern, and maybe tomorrow I need to add or change it, and that's okay because I have emergent architecture. I am open to changes. I welcome them as long as it adds value to the product and keeps me going in the right direction. Then change is actually good. So next, let's talk about separation of concerns. We have all these boxes here, and each of these is kind of a concern. And that's not very pretty, but each concern is separated by code. So the reducer, every reducer file is named foo. Foo is like an example name, a dummy name. Foo reducer.js. All my reducer code is stored in files like this. The store actually has no code because it's only modified by the reducer. The action has two sets of code. I could call these different concerns, but right now I haven't separated them. I don't have a name for both of them. The actions file and the connect file. The view is in JSX files, and then the client and server methods are both actually written together in the same file called foo methods. Well, there's many methods, right? So there's a quote method, a shipment methods, user methods, and so on. But they all end in methods. And they run on both the client and the server. And then we have data code, which is in collection files. This is also isomorphic between the server and the client. This is just my view on how the concerns get separated, but tomorrow we may discover more concerns. And some of those might be database tasks that run hourly or daily, integrations, file storage, server rendering. There could be any number of concerns that get added, but as they get discovered, we should be sure to separate them in order to maintain this logical distinction between all the code. Okay, next I'm going to show you, I did some programming, and we will look at, it's about a 1-hour video. I will shorten it down, I'll speed it up, and we'll talk a little bit about some of the files I'm editing and how they are respecting separation of concerns.